Okay, so this is section 19.2, the only other section in this chapter, balancing redox equations. Now, here's the thing. This is, right here, the oxidation number method, that is another way to balance equations. Okay? The other way I've taught you is fine, but you need to go through this, you need to see this to see where it's coming from. Okay? It's actually not that difficult. It just takes some time to get used to it, but we'll go through it. Okay? These are the 5 steps. Okay? See if that makes it clear. Okay. You assign oxidation numbers to all atoms in the equation. You identify the atoms that are oxidized and the atoms that are reduced. Okay, you look at what the change is in their electrons. You determine the change in oxidation number for the atoms that are oxidized and for the atoms that are reduced. Okay, you make the change in oxidation numbers equal in magnitude. This has got to match up by adjusting coefficients in the equation. If necessary, you use the conventional method to balance the remainder of the equation. Okay, again, at that point it may seem like, why do this? But we're going through it. It'll help make some things a little clearer. Okay, so I'm going to work through the example, showing you how I do it here. So the example, by the way, is on this page here, 19.3. All right. So let's see, zoom out. It's a little slow on the zooming. There we go. So this is my reaction, and it wants me to balance it. All right, Cu plus HNO3 yields Cu NO3 2 plus NO2 plus H2O. Okay? Conventionally, this one would be kind of confusing to balance the other way, for sure. Okay? The first step, assign oxidation numbers for each atom, or each element, excuse me, in each molecule. So, each one's going to have one. This is neutral. It's just a metal ion, so it's 0. Okay, here, okay, that's H plus and NO3 minus. Now, once we go through that, the H ends up with plus 1. Okay, and when we do this, the NO3, we do it like we do normal. Okay, it's like we did the other way. So NO3 minus. All right. Let's figure out the oxidation states of the N because we know what O is. O is a -2. So what's the oxidation state of N in this one? So that's N is something plus 3 O's, and that's 2 minus. That has to equal a -1 charge. So that's something plus 6 minus 6 equals -1. N is plus 5. Okay, so plus 5. Notice plus 1 plus 5 minus 2 times 3. That adds up to 0. Okay, going into this one, it's ionic. Okay, so remember that breaks down to Cu, and that's 2 plus. Now, in this, it actually still has the same charges. So the N is still 5 plus. It's just there's 2 of them. The O is still -2, but there is now 6 of them. Okay? All right, and then we have NO2. We do it the same way. Oxygen's going to be -2. So that's Cu NO3 2. So that's plus 2 plus 5 minus 2. Okay, here NO2, that's a -2 on the oxygen, and there's 2 of them, so that means this has to be a positive 4 on the nitrogen. And then H2O. O is more negative. It's 2 minus, so that's H2O. That's a 2 negative, or negative 2, excuse me, on the oxygen. And that's a positive 2 on the hydrogens. Okay? Now, that's all their oxidation states for each element in these compounds. So, which ones are oxidized, which ones are reduced, and which don't change? Okay, looking at each one. Look at copper. Copper goes from copper to copper 2 plus. It was oxidized. It lost electrons. Okay, hydrogen. And this goes from plus to, if we look over here, well, it's actually, this is a plus 1, excuse me, there's 2 of them. Alright, it's still hydrogen plus. It didn't change. Okay. Nitrogen goes from plus 5 to it is still plus 5. There is no change. Okay. And then we have oxygen. Okay. Oxygen goes from negative 2 to negative 2 here and negative 2 here. And still negative 2 there. So it did not change. It's still 2 minus. Okay. So, all right. Oh, I'm sorry. This nitrogen didn't change in the polyatomic ion. This one did. This nitrogen did. So we did have an N5 plus that went to N4 plus. Okay, it was reduced. Remember, if you have to have oxidized, you have to have reduced. That's why I was confused for a second. I didn't have my reduction. Okay, so the copper was oxidized. One of these nitrogens, now the one that stayed is NO3s, those stayed the same, but one of them got moved over and got reduced. It got an electron added to it. Okay, so that's where we have our reduction. All right. Now, determine the change in oxidation number for the atoms that are oxidized. That's what we just did, right? So this, it goes from 0 for copper, 0 to 2 plus, and this went from 5 plus to 4 plus, right? So it added 2. Here it subtracted 1, right? All right. Make the change in oxidation numbers equal in magnitude by adjusting coefficients in the equation. Okay. This is where it gets a little weird. Because you change the oxidation number, because the change in oxidation number for N is -1, you must add a coefficient of 2 to balance. Okay? We need this to be balanced. So this needs to be times 2 to match up to that. Okay? Because it has to, if we lose, those electrons have to be counted in here. And so 2 of these electrons are going to 2 of these nitrogens. And so what does that mean? Okay? All right? This coefficient applies to both of the nitrogens. Okay? It'll apply to on this side and on this side. Okay? So we still have Cu plus 2HNO3 yields Cu NO3 2 plus 2NO2 plus H2O. Okay? Okay, so it has to apply to both which it came from and which one it went to. Okay, that's why we multiply both of these by 2 and not just this one. It has to be, where did the nitrogen come from? Well, there's only one place it could have come from. Okay, so you would multiply that to make this change add up to 0. Okay, and then when you finish balancing your reaction, all right, you're going to, at this point you do it like normal, and so you end up with Cu plus 4HNO3 yields Cu NO3 2 plus 2NO2 plus 2H2O. Okay. It seems like, why couldn't we do that from the beginning like we normally do? We could. What this does, why this is useful, is this helps take away some of that guessing game as to where to start. Okay? This tells you, okay, well, that needs to be balanced. It has to be. And so if you balance that, that allows you to have a head start on balancing the rest of it. Okay? So, why don't we practice one? All right. Number 15. Okay? HCl plus HNO3 yields HOCl plus NO. Write that, NO plus H2O. Okay, so here HCl plus 1 minus 1. HNO3, H is plus 1, and the N, we already did these. Oh wait, oh. That was, yeah, NO3 minus, yeah, same thing. Okay, so we have N, so that's going to be plus 5. O3, the O's have a negative 2. Yields. This one's a little different. This is a little different here. And the H2O we know. The hydrogens have a plus 1, and the oxygen has a negative 2. Okay, here an HClO, okay, is actually hypochlorite, okay, which is ClO minus. Okay, and that's H plus. So the H has a 1 plus ion, oxidation number. And here we got to figure that out, right? Work it on the side. ClO minus. Okay, so it has to equal a negative 1. The oxygen is always going to be 2 negative. So 1 oxygen. Cl is going to be our number we don't know. So we have what plus negative 2 equals negative 1. Has to be positive 1. Okay? Cl is a positive 1, and O is again 2 minus, or negative 2, excuse me. I keep messing that up. NO, we can do it over here. Which one's more electronegative? O. Okay? So that means that O is going to be 2 minus, meaning N has to be 2 plus. It doesn't have much choice. It's 1 plus 1, so that has to equal NO, which is neutral. 2 plus 2 plus a negative 2 equals 0. So here we have plus 2, minus 2, and again plus 1 and minus 2. Alright. So let's look at this. So we have H here and H here. These both have the same. Okay, and an H here and an H here. These both have the same. So there's no change in H. Okay? Let's do it like this. H, no change. Cl goes from Cl with a negative 1 oxidation state right here to Cl with a plus 1 oxidation state. It lost 2 electrons, so it was oxidized. Okay? The H we already covered, there's no change. The N, so we have N that is plus 5 going to N that is plus 2. Alright, so it gained 3 electrons, so it was reduced. The O's, no change in O's. Okay? Very rarely will O be different. It has to be a peroxide or bonded to fluorine. Okay? Alright, so here we have our element that was oxidized, chlorine, and our element that was reduced, nitrogen. Alright? So, what's the multiplier here? What's going to make it the least common multiple? 6. So I'm going to need to multiply this one times 3. And this one times 2, right? Because what's the change? So here we have lost 2 electrons, gained 3, so that would be a loss of 6 electrons, so it would be plus 6, and a gain of 3 electrons times 2 equals minus 6. Balanced, right? Okay, so these are my multipliers. Now I'm going to put that in front of. Where's the Cl minus? Where's the Cl? There and there. So it'd be 3HCl plus HNO3 yields 3HOCl or HClO, either way, plus NO plus H2O. Okay? And then the nitrogens get times 2. So there's only 2 places they're there. So there and there. Okay? Now, let's see if that's balanced right now. Alright? So HCl, N, and O. HCl, N, and O. 3 plus 2, 5. 3 chlorines, 2 nitrogens, 6 oxygens. Here, 3 hydrogens plus 2 hydrogens, that's 5. 3 chlorines, 2 nitrogens, 3 oxygens plus 2 oxygens plus 1 oxygen. So it's balanced. Okay? Didn't have to do anything beyond that. This is why it works. Okay? I'm going to work one more out. Work out 17 there. Alright. No, it's 16, excuse me. Tin chloride, so SnCl4 plus Fe yields tin chloride plus FeCl3, excuse me. So, what's happening here? It's not balanced, we know that. What are the oxidation states? Well, iron here, that's 0. Okay? The chlorines are almost always going to be, especially when they're attached to a metal, they're going to be 1 minus. Okay, so that's a negative 1, and that's a negative 1. And as well here. So, the metals are the what's being oxidized and reduced. Okay? So what does the charge on this tin have to be? So SnCl4. Okay, what does that charge have to be? Well, that's 4 Cl minuses and then 1 Sn, we don't know. That has to be neutral, right? So what plus a negative 4 equals 0? A positive 4. So that's plus 4 on that tin. This one's going to work the same way. That's going to be plus 2. Here's 0. Here I have 3 chlorines. Meaning this is going to be plus 3. Now, if you remember how was it difficult to find the oxidation states of these transition metals, this is where they're coming from. Okay, this is where we're getting it. This is iron 3 chloride. Okay, this is tin 4 chloride. This is tin 2 chloride. Okay, that's where it's coming from. So, whatever things, let's look at each. So, tin goes from plus 4 to 2 plus 2, excuse me. Okay, it gained 2 electrons because it was reduced in number. Okay, by 2 electrons. Iron goes from 0 to plus 3. So it lost, was oxidized by 3 electrons lost. Okay, what's the multiplier here? They want to get to what times what is the least common multiple of these? 6. 2 and 3 is 6. Okay, so this one, tin's going to get multiplied by 3, and iron's going to get multiplied by 2. And -6, plus, and it's a +6, equals 0. Okay? Okay, remember, this lost electron, so this is a loss of 3 electrons, so it's more positive. Okay? I know that can be confusing the way that was written there. So, what does that mean? Okay, well, everyone that has tin, that gets multiplied by 3. Everyone that has iron gets multiplied by 2. So we have 3 tin 4 chlorides plus, and then iron gets multiplied by 2, 2 Fe yields 3 tin 2 chlorides plus 2 iron 3 chlorides. Let's check it. All right, tin, chlorine, iron, tin, chlorine, iron. So that's 3, 4, and 2. 3, 1, oh no, excuse me, not 4, 12, 3 times 4. 3 tins, 6 chlorines plus 6 chlorines, that's 12 chlorines, and then 2 irons. It's balanced. Okay? The hard part is figuring out the oxidation states. Follow those rules on that page. Okay? That will help you. So, breaking it down to net ionic equations can actually help it out. Alright, that kind of breaks down if the stuff doesn't change. Remember those spectator ions? If they're just spectating, they're not changing. If they're not changing, they're not being oxidized, and they're not being reduced. Meaning, you don't have to really worry much about balancing them. But, let's look at this and see. So, we are given the net ionic redox equation. We're going to do it basically the same way. Alright, so, number 19. Okay. H2S plus NO3 minus yields S plus NO. Now NO we already done, plus 2 minus 2. S here, that's 0. Here, what we do, which one's more electronegative? The sulfur. And hydrogen's almost always going to be 1 plus. So that's plus 1, meaning there's 2 plus 1s. So this has to be minus 2. And this, we've already figured this one out, plus 5 and minus 2. Okay? Alright. Now, here's the thing. Where's hydrogen? Where did it go? Okay. Okay. So, where I was. Where did hydrogen go? Notice it's not on this side. But it does tell you in the problem, okay? It does tell you in acid solution, okay? What does that mean? If it's acidic, it's giving off hydrogen ions. If it's giving off hydrogen ions, that means on the other side is going to be hydrogen ions, okay? If it's in acidic solution. Which, by the way, if it was in basic, there would be hydroxide ions added to that side. It's not for this one. Alright, so that's the part that's missing here. So here hydrogen is plus 1 there, and it goes to hydrogen plus 1, no change. Alright, sulfur goes from a -2 to 0. It lost 2 electrons, so it was oxidized. And here, oxygen goes from a -2 to a -2, no change. And then nitrogen goes from a +5 to a +2. It gained 3 electrons, so it was reduced. Okay? What was lost has to match what was gained. It's the least common multiple of 2 and 3. 6. Lost electrons, it's positive, so that's times 3 plus 6. Gained 3 electrons, that's negative, so times 2 minus 6, that adds up to 0. So the sulfur compounds get multiplied by 3. The nitrogen compounds get multiplied by 2. Okay? So that's going to be 3 H2S plus 2 NO3 minuses yields 3 sulfurs plus 2 NOs, and then plus hydrogen ions because those are still there. Now, it's an acidic solution. Is this balanced? It's not going to be exactly because, again, we have to match for that. So I have hydrogen, sulfur, nitrogen, and oxygen. Hydrogen, sulfur, nitrogen, and oxygen. Okay? So I have 3 sulfurs, 2 nitrogens, and 6 oxygens. 2 times 3. Alright, hydrogen's over here. I have 1 right now. Okay, but that's easy to change. 3 sulfurs, 2 nitrogens, and 2 oxygens. Alright, so what comes together is the hydrogen's easy to balance, so let's just put 6 right there. That'll balance that. Where's our problem? Our problem lies with the oxygens here, right? So where are they going? Alright. Hold on 1 second. Alright, sorry. So again, we had our hydrogens, and we're looking for oxygens. We also have to add in water molecules. It's in an acidic solution, so if there is hydrogens, there are waters. Okay? If there's hydrogens and oxygens. So then that means we need some number of H2Os, right? So then I have that wrong. So I have 3 hydrogens to start with. I need 6 oxygens. 2 are coming from here and 1's coming from here. That means I need 3 no, excuse me. 4. 2 plus 4, 6. Okay? And that means I need 8. Oh, 4 times 2 is 8. Okay, so I don't need hydrogens on this side, but what I do need is hydrogens on this side. Again, this is an acidic solution, so we just assume there are these here on both sides, honestly. So, if there's 8 hydrogens here, 6 from there, I need another 2 here. Okay? So, that makes it balanced. Let's go through another one. Okay? Number 20. Cr2O7, 2 negative, plus I negative yields Cr3 plus I2, and it's in acidic solution, meaning I can add H's and waters as I need. Okay, so because we're going to have to do that to both sides probably. What side you have the H's to is probably going to be the opposite the side you have the waters to. Let's get the oxidation numbers first. Okay, here we're good, that's plus 3. Here we're good, that's 0. We know that. Here, negative 1. Cr2O7, 2 minus. That's the problem. Okay, so it's going to equal a negative 2 total. Oxygen, again, it's not a peroxide. It's not fluorine. So that's always going to be 2 minus. So that's 7 oxygens at a negative 2 charge. and I have two chromiums, excuse me, at some charge. Okay, so that's a negative 14 from the oxygen. And 2 times some number plus that equals negative 2. Well, it needs to be negative 12. It needs to be a positive 12, right? So that means that's what's positive 12 divided by 2 plus 6. Okay, so the chromium is at a plus 6 charge. Oxygen, again, minus 2 charge. Okay? So, that makes a pretty color too, by the way. So, here, this reaction, let's look at what we got going on here. So if Cr is going from plus 6 to Cr with a plus 3, right? It's gaining electrons. It's losing. It's being reduced. And it gained 3 electrons, so it was reduced. Oxygen, there's a negative 2 there. And oxygen isn't on this side, meaning I need to add water. And it is also, again, at a negative 2 and plus 1 for the hydrogen. Okay, and since there's hydrogens here and not here, I have to add hydrogens there. Okay? Add H plus and H2Os as needed. Okay? Wherever you need them, they're there. Okay, there's enough of them. So, again, negative 2. Now, that, no change. I goes from a negative 1 to I of 0. It lost electrons, lost 1 electron, so it was oxidized. Okay? What's the least common multiple of 3 and 1? 3. So we don't multiply the chromium by anything, but we do multiply the iodine by something. Okay, so that's times 3. So that means that Cr2O7, 2 negative, plus 3I negative. Again, this doesn't change right now. And then we do 3I2. Okay. Which immediately we can notice 3 times 2, that's going to be 6. I'm going to need 6 of these. So I can already scratch that out. Just put 6. It's got to match up. You got to have the same amount. Okay? So, what else are we missing? We're missing the hydrogens and we're missing the water. So I have H plus how many Cr2O7s plus 6 I minuses yields. How many Cr3 pluses? It's going to be at least 2 plus 3 iodine molecules and then plus water. Okay, if the oxygens went somewhere in an acidic solution, they attach to hydrogen to form water. Okay, so let's balance it. H, Cr, O, and I. H, Cr, O, and I. Okay, we have, right now we have 1 hydrogen, 2 chromiums, 7 oxygens, and 6 iodines. Right now here we have 2 hydrogens, 1 chromium, 1 oxygen, and 6 iodines. Okay, the iodines are good. Fine with that. Now, I need more hydrogens over here, but let's see. This is going to change because I need 7 oxygens. The only way I'm going to do that is if I put a 7 in front of the water. That's 7 oxygens now, but now that's 14 hydrogens. Meaning, I need a 14 in front of that. And a 2 in front of this to balance that. And now we're good. Okay? I know you're going to have questions about this for sure. I'm going to make some problems more like this for y'all to work, and I'll work out some more in another video. Okay? Half reactions. Okay, so half reactions are looking at just the oxidation or just the reduction. Okay? It's just like that. So, and it's looking at it in terms of electron movement. Okay? So here they use the term species as any kind of chemical unit involved in a process. Okay, chemical species. So here, let's look at this reaction. 2 Fe plus 3 Cl2 yields 2 FeCl3. That's iron 3 chloride, by the way. So here, the oxidation state is 0. Here, the oxidation state is 0. Those are molecules. Here, the oxidation state for chlorine is a -1, meaning the iron is plus 3. So here, we look at Fe at 0 to Fe at a plus 3. Okay? What happened? It lost 3 electrons, right? And so that means it was oxidized. Okay, we can show that though. We don't have to just write like this. What we can do is say, where did those electrons go? Well, they went somewhere, but for the moment, what we can do is put them in place. Plus 3 with a little electron symbol. Okay, that's a half reaction. That is the oxidation half reaction. It's only half of what happened, but it's half of it. All right? Now, looking at the other part, which has to be the reduction, right? So we have chlorine that went from 0 to, and, oh, and that was, excuse me, 2 and 2, 2 and 2, and therefore 2 times that, so it'd be 6 electrons. You gotta have it balanced as well, excuse me. But chlorine, so there are here 3 chlorine molecules at 3 chlorine molecules at a 0 charge go to a total of 2 times 3, so that's 6 chlorine minus molecules, -1. All right, makes sense, right? 3 times 2 is 6, 6 zeros to 6 -1, so that will gained total of 1 electron per chlorine, right? So that means 6 electrons total. Okay, so that's 3 Cl2 yields 6 chlorine -1s. Excuse me. Where did it gain them from? Well, they had to have been on this side. So I wrote that wrong. 3 Cl2 plus 6 electrons. They reduced that to 6 chlorine -1s. Okay, that's the reduction half reaction. Okay. Now you see, they didn't do it like that. They just simplified it like I had it the first time. That's what I should have done. Okay. Okay, let's discuss half reactions again. We're using redox reactions. And so it's 2 halves. There's the oxidation half and the reduction half. Let's walk through this first one here. 2 Fe plus 3 Cl2 yields 2 FeCl3. This is oxidation number of 0. This is the oxidation number of -1. Here, chlorine is -1, meaning iron has to be +3. Okay? So, what's happening? Iron is going from iron 0 to iron +3, right? Well, it lost 3 electrons, right? So it was oxidized. There's another way to say it lost 3 electrons. You add electrons to the right side. So Fe0 is Fe +3 electrons. Okay? Now chlorine, you have chlorine molecule that's neutral. It goes to 3. No, I'm sorry. It goes to Cl minus. Now there has to be 2 of them, right? Because 2 breaks down. So then it gained 1 electron. Okay? But 2 of them gained it. Okay? 2 gained, so it's a total 1 electron each. So a total of 2 electrons gained. So we had to gain them, they had to start on the left side. So that's Cl2 plus 2 electrons yields 2 chlorines with a -1 charge. Okay? That's the oxidation half reaction. This is the reduction half reaction. Okay? That's what half reactions are. You're just splitting it up, and I've already done this somewhat in a couple of the others. Split it into the oxidation and the reduction. Okay? Now, redox reactions that oxidize iron, there's a lot of ways you can do it. All of these have the same oxidation half reaction. They turn iron into iron 3+, which will actually give you that red, I believe it's the red rust. There's 3 types of iron rust. There's a yellow color, there's an orangish color, and there's a redder color. I believe the iron 3+ is the redder color. And so here you get your different things and what happened to this. These were all reductions, okay, but just different things were oxidized that iron, okay? All right. Okay, now we're going to learn how to balance equations using the half reaction method. It's a lot like the oxidation method, but just using the half reactions we've already just learned about. So, let's start here, and we'll do this one up here in the top here. It is, maybe hard to see, KMnO4 plus SO2 yields MnSO4 plus K2SO4. Now notice this is aqueous, this is gas, this is aqueous, and this is aqueous, and it is in acidic solution. So we're going to have to add H's and waters if need be. The first step is you've got to actually get to the net ionic equation. Okay, so you got to break all this down. So that's K, and its oxidation state is 1+. I will do +1. And then MnO4, that has to be -1. Now, SO2 is a gas, so we don't break it down. Yields there, Mn. Now, SO4 is 2-. We know that. And then, so that means that manganese, in order to only have one of those, has to be +2. Alright? And then here, we have K2SO4. There's 2 Ks that have a +1 charge. Okay? And then we have 1 SO4, which has a 2- charge. Okay? So, let's finish writing our oxidation states. Some of them are already finished. Okay, so here, K +1, yeah, has a +1 oxidation state. MnO4, -1, okay? Let's break that down. So it has to equal -1. Oxygen's always 2-, so there's 4 oxygens at a 2- charge. Mn is at something, so something plus a -8 equals -1. So that has to be +7. Oxygen -2. Again, oxygen is -2. So that means in order for this to balance, 2 times -2 is -4. That has to be +4. Alright? Same thing. That charge we're good with, so that's +2. This, SO4, 2 minus. Let's break that one down. Okay, so that's to equal -2. 4 oxygens, always add a -2 charge, and then the sulfur's at something. So that's a -8 plus something is -2. It has to be +6. So this sulfur is at +6. The oxygen still is at -2. That's still +1. And again, we have the sulfate over here. Okay? Same thing. +6 and then -2. Okay? And you could actually, I believe they do it here, bring those together. But let's look at this. Okay. That's a lot to look at. What changed? Okay. Well, K ends up being a spectator ion. Okay. K is a spectator ion, so it goes away. So our reaction that's left is MnO4, -1, that's +7, -2. The oxygens don't change here. Plus SO2, so that's +4, -2, yields Mn, 2+, so that's +2, plus SO4, 2 minus. And there's actually 2 of them, right? So we don't need to write it again. It's just there. We're going to end up adding it into balance and things like that. It's just there. So that sulfur in that one is +6, and then that is a -2 on the oxygen. So what changed? Magnesium went from +7 in the MnO4 -1 minus to Mn +2. Okay, so it went from +7 to +2. Alright, it gained electrons. How many did it gain? It actually gained 5 electrons, right? So that was again reduced. Okay, what happened to the sulfur? Sulfur and SO2 went from +4 to sulfate to end up with a +6. It lost 2 electrons. So it was oxidized. Okay? Alright, so we know what was reduced, we know what was oxidized. Alright, let's finish our half reactions. Okay? So if it gained electrons, that had to be over here, right? So M N O4 negative plus 5 electrons yields Mn 2 plus. Okay? That's the oxidation half reaction. And from now on, I'm just put HR period. Okay? Okay, and then so that's that, and then this one, SO2. It lost 2 electrons. So it goes to SO4, 2 minus, and it's plus 2 electrons because it got lost. It lost on the right side. If it's gained on the left side. Okay? And so this is the reduction half reaction. Okay. Now, in order to balance this, we have to have the right number of electrons, correct? So, what's the least common multiple of 5 and 2? Okay? That's going to have to be oh, no, I'm sorry. Okay, so here it says balance its atoms and charges in the half reactions. Okay, we're at this point here. We use those rules. We got these. Now, the thing we have to know is where to add the hydrogens and the molecules. If we need to add oxygens to one side, we use water. If we need to affect a charge on one side, we use the hydrogen ions. Okay, so let's look at this first one here, the reduction half reaction. So SO2, right now, I need 2 more oxygens, right? So I'm going to add 2 waters. Okay? Yields SO4 2 minus plus 2 electrons. Now I added 4 hydrogens here. I have to account for that charge change. That also, so plus 4 hydrogen ions. Okay? That will balance the charges. Okay? Then we go to magnesium oxide. So, alright, so that's that. So that's the reduction half reaction. And so let's look at the oxidation half reaction. MnO4 minus plus 5 electrons. I need more oxygens on this side. So I need to add H2O, but how many? I need 4 oxygens, so I add 4 waters. That gives me 8 hydrogens plus 8 H plus. Balance it out like that. Okay? Now, alright, adjust coefficients so that the number of electrons lost in oxidation, 2, we lost 2 electrons in oxidation, alright, is equal to the number of electrons gained in reduction, again 5, so it's the least common multiple of 2 and 5. It is 10. So that means that 5 times the oxidation reduction, 2 times the oxidation reaction, 2 times the reduction reaction. So here again, this lost 2 electrons, so it's times 5. This gained 5 electrons, so that's times 2. Okay? The MnO4 one, that's times 2, right? Everything in there times 2 gives us 2 MnO4 minus plus 10 electrons plus 16 hydrogens yields 2 magnesium 2 pluses plus 8 waters. Okay? So that's that part. Let's do the reduction. So that's 5 times SO2 plus 2H2O yields SO4 2 minus plus 2 electrons plus 4 hydrogens yields. So that's going to give us 5 SO2s plus 10 waters yields 5 SO4 2 minuses plus 10 electrons plus 20 hydrogens. 5 times 4 is 20. Bring it all back together. Okay. And this is the long part. Add the balanced half reactions by simply, or simplify by canceling or reducing like terms in both sides of the equation. Put it back. What's on the left side of the reaction goes on the left side. Okay? So this combines with this on the left side. So I have 2 MnO4 minus plus 10 electrons plus 16 hydrogens plus 5 SO2s plus 10 waters yields the other side added together 2 Mn2 plus 8 H2Os plus 5 SO4 2 minuses plus 10 electrons plus 20 hydrogens. Alright, that's the long thing right there. Okay? Now we got to simplify that. Alright? So, cancel out what we can. 10 electrons, 10 electrons. Good. You have that balanced. Cancel that out. Alright. 5 SO2s, 5 SO4 2 minuses, 8 waters, 10 waters, 20 hydrogens, 16 hydrogens. Look at the net. What do you need? Okay, I have 16 hydrogens on the left, 20 hydrogens on the right. So that means on the right side, I need plus 4 hydrogens. Okay, I don't need them on this side now. That is a net on that side. Alright, 2MnO4 minuses, we need those. Okay, 5 SO2s, those have to be there. Alright, 10 waters, 8 waters, a net of 2 waters on this side. Okay, that's the rest of this side. And then I have 2 Mn2 plus. Got rid of that already, and that goes down to 2. That goes down to 4, put it like that. And then 5 SO4, 2 minuses. Okay. Is that balanced? Let's look. Mn O S H Mn O S H Mosh. Okay, 2 Mns, 8 oxygens plus 10 oxygens plus 2 oxygens. 8 plus 10 is 18 plus 2, 20 oxygens. Sulfurs, I have 5. Hydrogens, I have 4. 2 Mns, 5 sulfurs, 5 times 4, that is 20 oxygens, and I have, oh, my 4 hydrogens over here, sorry. Okay, 4. That is the balanced net ionic equation of that thing at the top. That's a lot to do, okay? I understand that. You would not have many of those on a test. Anyways, your tests are technically take home. So I'm going to do one more from the ones at the bottom, number 23. Okay? And then once you leave the balance equation in ionic form, C2O7 2 minus, Cr2O7 2 minus, plus I negative, this is aqueous, and this is aqueous, yields Cr3 plus, aqueous, plus I2, and that is solid. So you would have a precipitate in that reaction, and it is in acidic solution. Okay. So we're already at the net ionic. We didn't have to actually write the net ionic. It's already there for us. So right now we just got to get the oxidation states right. Then we do our half reactions. So I have Cr2, O7, and that's going to Cr3 plus, right? So what is the oxidation state of chromium in this? If you don't remember, let's do it again. So Cr2O7 2 minus. Total has to equal negative 2. There's 7 oxygens, we have a 2 negative charge, and there's 2 chromiums, which have, we don't know. So 2 times what? Plus 7 times negative 2 is negative 14, equals negative 2. Again, that has to be a plus 6. So we have plus 12 plus a negative 14 equals a negative 2. Okay, so this chromium is at plus 6, and this chromium is at plus 3. So, this is a gain of electrons. So it gained 3 electrons. Okay, so that means that we have Cr2O7 2 negative plus 3 electrons gives me Cr3 plus. That is our first half reaction. Okay, and that is the, again, reduction. That's the reduction half reaction. But it's not balanced, is it? Because I have oxygens here and not here, meaning I must add waters to this side. Remember, it's in acidic solution. So that's Cr2O7 2 negative plus 3 electrons yields Cr3 plus plus H2Os. Now how many do I need? So, and I have to add hydrogens to this side. Okay? I need 7 oxygens, so I need at least 7 of those. That means I have to add plus 14 hydrogen pluses. and then we need 2 chromiums, okay, to match that, okay? And in order to match that, we got to multiply that, because then we need 6 electrons. Okay? But we'll get to that in a second. Cr2O7 2 minus plus 3 electrons plus 14 hydrogens. Let's see there, plus 7 waters. Okay. Let's look at the oxidation reaction. And so that is the iodine. So we have I negative goes to I2. Now if you look here, we don't have to add waters or anything like that. So it's at a 0 charge here, so that it is I, and there has to be 2 of these. Okay, in order for that to balance. So that's 2 I's, negatives. It loses an electron, so it loses 2 electrons. Okay, because that is the oxidation. Lost 2 electrons. Okay. Now, I have 2 electrons here, I have 3 electrons here. What is the least common multiple of 2 and 3? 6. So that means this entire thing is going to get multiplied by 2. This entire thing is going to get multiplied by 3. So that gives us 2 Cr2O7 2 minus plus 6 electrons plus, again, times 2, so that's 28 hydrogens yields 2 Cr3 pluses plus 14 waters. We multiply that by 3, we get 6 iodine ions yields to 3 iodine molecules plus 6 electrons. Now bring them together. Okay, everything on the left goes on the left. Cr2O7 2 negative plus 6 electrons plus 28 hydrogens plus 6 iodine ions yields, right at the top here, so 2 Cr3 pluses plus 14 waters plus 3 iodine molecules plus 6 electrons. What's the same on both sides? I have 6 electrons, that cancels. I have 28 hydrogens here. That's got to stay. There's no hydrogen ions over here to get rid of. Waters say the same thing. Alright? So, what are we left with? 2 Cr2O7 2 minus plus 28 hydrogen plus ions plus 6 iodine ions yields 2 chromium 3 plus ions plus 14 waters plus 3 iodine molecules. Is that balanced? 4 chromiums, 2 chromiums. No, this needs to be a 4. 14 oxygens, 14 oxygens. 28 hydrogens, 14 hydrogens. 14 times 2, so that's 28. We're good there. 6 iodines, 6 iodines. Okay, so this is our final reaction. It's a lot to do, but it can be done. Okay, we're going to stop here, and then I'm going to make another video working on some of the problems